last time, if you remember, we are left off with we finished implementing the Keithley class. So the Keithley class, it had an interface. We implemented a few basic features of the Keithley, a few basic functions. Just this to the bottom there. We implemented a few basic functions about setting the source ranges, limits, setting the voltage, and measuring the current. And if you remember, what we wanted to do was to do a simple measurement, and the measurement looks like this. Let's see if I can maybe get out the desktop. So if you remember, the simple circuit that we had was this one here. So we have a photoresistor, which is the thing that we are measuring. We're using the Keithley source measuring unit to measure it. So we apply a voltage and we measure the current. So that's kind of like a resistance measurement, and then we can monitor the current in real time as well. And on the other side, we have the Tenma programmable power supply. This is a basic power supply that you will find under many different brand names. So this is the Tenma one, and it communicates with the computer with a serial interface. And we're using the Tenma to supply power to a green LED. The green LED emits light, and the light hits the photoresistor. And this is supposed to change the value of the resistance of the photoresistor. And this is a sort of very simple, basic experiment that we'll be doing. So if you look at that in terms of what we've got here on the table, is that, well, you can't quite see it, but the LED is on this side, it's transparent, so you might not be able to see it very well from Zoom, but it's a transparent case LED. So once we supply power, this should light up green, and right in front of it, this is the photoresistor. The photoresistor will pick up the light and in principle change its resistance. So this is the kind of experiment that we want to do. So last time we got to the point of defining all the features of the Keithley as an instrument. So the Keithley is pretty much done, and I did sort of the same thing with some basic communications with the Tenma power supply. This time I'm not going to go again through the same thing. So for the Tenma, I've already prepared a script that lists all the basic features that we need. So I'm going to close this file, and I'm going to so with the tutorial code, I'm going to bin this, and I'm going to copy sort of an already prepared version from my files. So I'm going to copy paste this. Let's see. Okay, so desktop, actually, that's what I wanted. Tutorial code. I'm going to paste here the files for the Tenma. So we can open this with Qt Designer. There we go. I'm going to click open desktop. And I have a very, very simple user interface. I mean, generally with the serial instrument, that's the case. You will have some very basic commands that you actually need. Although, well, they actually could be quite complicated. It's not a feature of specific to serial instruments. But anyway, what we've got in this case, we just want to use the power supply to provide some current. So I'm not actually reading anything from the power supply this time. So the only thing I'm interested in is the voltage that I want to set, the current, and whether the output is on and off. And that's all I've got here. So this power supply, the way it works is that we can operate in a constant voltage or a constant current mode, depending on what is sort of highest in the two settings. So if I say that I want a current of, say, for example, 20 milliamps, I can turn on the power supply, and the power supply will make sure that I never exceed 20 milliamps. But I can go below 20 milliamps. But if I start, for example, to supply well, I don't know. Well, you'll see that in a minute. But if I start to supply a voltage that would lead the system to have a more current than 20 milliamps, the power supply will actually not do that. It will limit its own voltage internally so that the actually the voltage that's actually being output is not the one that I asked, it's the one that is required to reach a current of 20 milliamps. So if you're below that limit, then it acts as a constant voltage supply. So it will output the voltage that you are asking for. So in my case, from the specification of this LED, it's a very small LED. So it works, it turns on around 2 volts and it has a maximum rating of 30 milliamps. So I want to make sure that I never exceed 30 milliamps because otherwise it will probably get damaged. So whenever I will do the demonstration here. I'll probably set the maximum, the current as 30 milliamps. And if I do that, as soon as I turn it on, I can increase the voltage as much as I want, but the power supply itself is designed so it never exceeds 30 milliamps. So you'll see that in action very soon. So these are the few basic functions. As you can see, I'm not reading anything out of the instrument. And the code is here, so I'll just open that. Tenma code. So you see it's in total sort of 50, 60 lines, so it's not a long code. This is the Tenma class that we had, the same as last time. We had the Keithley class defined here. And in this class, we have a function to set the voltage, to set the current, and set the output, whether the output is on and off. So that's all we've got. And these commands that I'm sending, these are the sort of the command strings that I'm sending. The command strings you find in the manual of the Tenma equipment, which we had a look at last time. So these are the few commands that I'm using, and these are the commands related to the user interface. As you see from last time, we're inheriting the properties of our Qt widget, and that's imported up here. We connect to the user interface. We connect the spin boxes. So these are the 2 spin boxes. And they're connected so that when I change the value of the spin box, this automatically calls a function to set the voltage or set the current. And when we press the push button, the output push button, it's a clickable push button again. So it has like an on and off state. And so if the state of the button is checked, is on, then we turn the output on. If the state of the button is off, then we turn the output on. So we can very, very quickly demonstrate this by executing the code. So I'm just going to shut this and execute the code. So this will pop up this very little interface. And if you now look at the Tenma that we've got here, I can, for example, set an output of, well, you see the Tenma. I'm sorry, it's all mirrored again. I haven't actually bothered to fix that. But anyway, you see that something is actually happening in the power supply. And as well, I can change the current. So this is, for example, a current of 30 milliamps, and it's set to 1 volt. So I can hit the output, and now it turns on. You see this red LED that turns the output on and off. And if I now start to increase the voltage, you should be seeing this reading here, that's the current. Right now there is no current because I'm at a voltage. Well, it's not detectable. It's below 10. It's below a milliamp, the current itself, because we're in the off state of the diode. So it's below a milliamp and we're not reading anything. But as I start to increase the voltage little by little, I should see at some point, probably around 2 volts, as far as I remember, there we go. I'm starting to see something. The current is still 0 from the reading there. But now, yeah, so now you can see, well, can you see? Well, there's I guess the green light is a bit faint. You see, well, you can see the reflection of it here at the bottom. So that's the green light on and off. And I can ramp up the voltage. And you see now we are actually reading something here. It's a 4. So we're now outputting 4 milliamps, and we can go up to 30. So I can rise the voltage, and that's about as bright as it's going to get. So we're now at 30 milliamps, and I can increase the voltage, but the power supply doesn't actually output more than 30. And that's what you can see here, that the output is always the same. So I'm going to drop this to maybe say 2 volts or something like that. and I'm going to turn the output off. Right, so that's as simple as it gets, I guess, in controlling instruments. It's just a simple power supply. So I'm going to shut this down, and now we're going to, well, there's no questions as far as I can see. Q&A. Okay, we're good. So we're now at the stage where, so we got our two instruments, we've got the Keithley, we've got the power supply, and now we want to implement the actual experiment. So how do you go about doing that? My suggestion here is that first, before you actually go to the lab, you sit down and you think what is it you actually want to do, right? So what's your experiment like? So I've thought of two things that I want to do with this experiment. One is a simple sweep, sort of a current voltage sweep. I mean, with this Keithley, I could directly measure the resistance. Okay, so that's the instrument allows me to do that, but I'm not going to do that. I'm going to pretend that I've got, for example, another power supply and a multimeter or something like that, a digital multimeter. So what I'm going to do is that I'm going to use the Keithley to output a voltage and measure currents. And I want to do a linear sweep over a range of voltages. So that's the first thing that I want to do. So that's going to be a type of measurement when I do the sweep. So I click a button and I want the sweep to run from whatever starting voltage to whatever stopping voltage, run the sweep with a certain step. And that's going to be the end of the measurement. So it's just sort of a predetermined fixed sort of measurement. And then the other thing that I want to do is I want to be able to monitor continuously the current. So apply a voltage across the photoresistor and start monitoring the current until I want to stop. Okay, so I'm going to do like a start button. We're going to start the experiment, and then there is no predefined script that is that tells the computer and the equipment when to stop doing stuff. It's me. I decide when I want to stop. So this is very useful when you're running an experiment and you don't have a preset set of things that you want to do. You want to see how your samples is responding, and you want to do things accordingly. Okay, so these are the two things that we want to do. And at the same time, I want to see some real-time data. Okay, so I want to plot the data at the same time. So we're going to go through these things. So to do that, the way that you will usually get these things set up once you start programming your own equipment is that now I've got the Keithley and the Tenma instruments all programmed, and I want to be importing these. I don't want to rewrite this code or copy paste this code in other scripts. What I want to do is actually import these as modules, so I can then start assembling experiments without redoing the same stuff that I had before. So we're going to make use of the interface that we prepared for the Keithley and for the power supply, and we're going to make a new interface, which is the interface of the experiment. Okay, and this interface will contain the stuff that's related to the experiment, and we're going to pop up next to it just the normal interfaces that we already programmed for the Keithley and the power supply. So I'm going to create a new file here, and I'm going to save it as tutorial code. So I'm going to save it as, well, photoresistor experiment. Okay. And actually, what else I'm going to do, and just this is purely to demonstrate kind of how this works, generally speaking, is that I'm going to group these. I'm going to put this in a new folder, which I'm going to call instruments. Okay, so the Keithley, the UI, and the Tenma, I'm going to put them in the instruments folder. This is purely for a bit of an aesthetic purpose reason, sort of to show you how you would normally import modules. So normally you would write in your lab, you might have code to control instruments, you might have some code to do analysis, you might have some utility code that does whatever other thing you might need. So something is not an instrument. This really depends on how you personally like to organize your work. But the same way that we import packages that are already pre-made in Python, like NumPy and pyserial and pyvisa or whatever, the same way we can import our own packages. To do that, you have to add the path. You have to tell Spider and Python where to look for the code. Okay, so this is what I'm going to do now. So I'm going to go in this Python path manager, and I'm going to add the path. You see here that I've got sort of my own code that I use in my own work. So I'm going to go look for a path, and the one that I want is here. And you would usually import, well, you have to sort of import intuitively, you have to import the sort of the folder that will contain all the other folders for all your code. Okay, so in this case, I'm going to import tutorial. So now that is in the paths that Python will look in to find libraries that I'm asking for. You don't see here all the libraries that Python has already installed and already knows where to find. These are sort of hidden from, these are all the additional paths that you as a user are adding, but NumPy, for example, is not installed in any of these. It's already installed in its own libraries. So I'm gonna do that, and then I can, usually when you do this, the first time you need to restart the console because Python will need to reinitialize itself. So here I can try to see if Python actually knows what I'm going on about. So I'm gonna go from tutorial. Let's see. We'll try. This is all being done live. So from tutorial code. And now you normally go for dot, and that is the directory, dot instruments. Dot instruments dot, well, now I'm going to open it so I can actually see what I'm trying to look at. So I'm going to open both. Instruments dot, and then now this is the name of the file without the dot py. 32612b import, and now I need to say what is it that I want to import. I mean, I can import it all. I mean, depends on the syntax and how you like to do it. I like to be explicit about the things that I import. So and I want to import this, right? And let's see if that actually works. Yeah, it works. It actually opened this thing. Now, this is not kind of what you want, because I imported a library, and it actually what it does when you import something, and is that basically it will execute the code that you import. Okay, but all I want is for it to sort of execute the class definitions, but I don't want it to actually do anything. Okay, so what happened here is that I imported successfully, clearly, from this code that I got, but because when I import, basically, what Spider will do, what Python will do, is that it takes all this code and it executes it all. And at the very end of it, you've got all this section where the code is actually doing something. I'm assigning a port, and so generally, this section of code is something that you only want executed when you're debugging the particular code that you're looking at. Okay, so there's a little bit syntax trick that we use in Python. To make sure that when we import a certain script in a different file, we don't execute the bit that's at the bottom, but we only import the classes, the class definitions. And so this is purely syntax. I mean, you can go and have a look online and what's the internal working of all this. But in this case, I'm just going to shut this down. And here, so you just have to sort of know that this is how it's done. Now, it's not in my notes technically, so I'll go from by heart, but otherwise we'll just look it up because I can't remember the. So what you want to write is if name equals main, then execute this. Okay, this is sort of a underlying sort of Python thing that. Every time you execute something, there's like a main thread that Python has, and this thread is called main. Okay, so what I want is basically for this code to be executed only if this script is the one that I'm actually executing. If I'm importing this in a different program, a different script, when I execute that script is the main. And so when the code starts executing everything from the top, it goes through the class definitions, then it gets here, but the name is not main because the main is what I'm executing at that particular moment. So it's going to skip all this part. Okay, so so you've seen how in the last. So I'm going to save this. So in the last code that I did, this produced the actual interface for the Keithley. So hopefully now if I execute this, nothing happens, okay? But what has happened is that I have imported the Keithley class. So now I can say, for example, my Keithley equals Keithley, and now it finds it. So it can auto-complete with tab because it's something that it's a class definition that the Python console can recognize. Okay, so remember that. So we're gonna put that in the Keithley code, but also in the Tenma code because we want both of them to be available. Actually, here I've already put it because obviously it's code that I prepared in advance, so it works already. So it's the same thing that we've got in the other script. Okay, so now basically I have checked that this works. So I'm going to copy paste that class definition, and I'm going to do the same for the Tenma. Well, yeah, can copy paste that. And here I'm going to go for 10. And actually, you can see that already as I'm importing, actually, here it's telling me that what are the classes available, what are the modules available in tutorial code instruments that are available are Keithley and Tenma. So I import the Tenma. And in this case, so I actually want to import two things, because if you remember the instrument itself and its user interface, these are two separate classes. So we want to import both. So that's what we're going to do. So here we've got the Keithley and then we have the Keithley user interface, okay, which we define as an underscore UI. So I'm going to do the same here. And I've got the instrument itself and the user interface, okay. So I'm going to import that, and right now there's nothing else I need to import. Now in this case, this is my experiment script. So in this case, I could put the if name equals main, but generally speaking, the experiment script is the one that you always want to execute yourself. Okay, so it's unlikely, at least in this case, that I'm going to import my experiment into another experiment. I mean, it could be done, but in this case, I'm not bothered about adding this bottom section again. So everything that is here, I want to be executed right here. So I'm not going to do that. So, and if you remember now from last time, we had all this little section of sort of functions that we need to generate the interface. And we have to create that again. And in fact, we have to, first of all, initialize the instrument that we want to use. One is the Tenma, and the other is the Keithley. My Keithley. Keithley, which is the normal one. And we need to copy paste the address. So last time there was someone asking sort of about the question about the address. So when you might have more instruments, and this is where this becomes very useful, this definition, because you only put the address in this bottom bit, but the address is something that is related to the class. So every time you call the class, you pass it the address of the instrument that you've got on your table right now, and someone else in another lab might have the same instrument but with a different address. So this is the way to sort of decouple the address from the class. Okay, so your colleague in another lab, they might use exactly the same code, but when they actually call the Keithley class to initialize it, they put a different address in their own code, even though the class is exactly the same. So I can paste this there. Now, we had last time, we had the UI app. This is something that we always need when we use Qt widgets. It's giving an error here because I need to import Qt widgets, and I need to do that explicitly, even though it's done here. So I'm going to import that here on the top. So we have the Qt widgets. So we are generating the user interface app. So I'm going to space that. And then we have the Tenma UI. and we are using the Tenma UI class here, and we're passing it the Tenma object that we created here. That's the Tenma instance that we're using in this particular experiment. And we're passing this to the user interface of the Tenma UI class. And then we have the Keithley UI. Keithley UI. And we take the Keithley, just going to copy paste. This is just right there. And here I'm passing it the my Keithley object. Okay. And then we have here, well, this is from before. We have the Tenma UI. We have to show the Tenma UI. And we also want to show the Keithley. Keithley UI. It's a variable dot show. And then finally, we want to execute the whole user interface experience. So I'm going to shut that, and we'll try and execute this. Well, in fact, yeah, this we'll use later. I'm going to leave this here for the moment. We're not using it right now, but as soon as we create the experiment, the interface, we're going to start using it. Okay, so let's see if this works. Let's just run it, and there we go. So we have the two interfaces. One is here, and one is here. Right, so within one script, I now popped up the two interfaces of the two instruments, and I can go operate them as I see fit. Okay, so I'm going to shut that down. So that's the first step that we've gone through. So now we should just sort of get down to business and get the experiment up and running. So for that, we go back to the design of the interface. So always the design of the interface is sort of intertwined with the development of the code that you are using it to control it. So I'm going to close that, and I'm going to create a new widget. So create a widget. So what is it that I want from this experiment? So the first thing that we're going to implement is the linear sweep. Okay, so we're going to put a sweep from a starting voltage and end voltage. We're going to implement a step and a button to execute the sweep and actually get it done. So I'm going to put this that way. It might not actually need to be that big. Right. So let's pick up the widgets that we need. So what we need, it will be a push button, definitely, somewhere to start to do the sweep. Then we're gonna need some values for the voltage. So we're gonna use the spin boxes. The voltage is a floating point number. So we're gonna use the double spin box as opposed to a normal spin box. So we're gonna use one for the starting voltage, one for the stopping voltage. And now let me just check if, yeah, and then actually, rather than the step, we're going to use the number of points, okay? This is just to simplify because we're going to use the linspace function later on to generate the arrays, and you can implement it however you see fit. It can be a number of points, and it can be a step. That might depend on the experiment you're running. For simplicity, this time, I'm going to use the normal spin box, yeah? So the spin box will be an integer. So now, I want to lay out this whole thing in a way that is sort of nice. So you right click and lay out, and I'm going to lay this all out vertically. But now within the vertical layout, I'm going to put a horizontal layout where I'm going to put all the different features that I need and the labels. So I'm going to put a label here. I'm going to put a label here. And a label there. So this will be the start in volts, the stop in volts, and points. So these now I have to assign a certain set of values that they can take. So let's see if I can separate it. So this, first of all, I'm going to rename. So I'm going to call this vstart double spin box. And in terms of the values that I want to allow it to take, decimals, we can leave as 2 decimals. That doesn't really matter. The maximum in this case, I'm going to set it to 20 volts. The minimum, I'm going to set it to minus 20 volts because the key can take positive and negative values, just the same for the V start. The step here, I'm going to put a 0.1, and the initial value, I'm going to put like a -1, for example. Okay, so this will be the default value that comes in. V stop, we're going to do exactly the same. I'm going to put a value of +1, a maximum of 20, a minimum of -20, and a step of 0.1. Okay, and here on the very top, I'm going to put V stop double spin box. So V stop, V start, and this is the number of points. And points spin box. And here we go down, and we're going to put a minimum of, well, at least 1 point, because there's no point of any measurements with less than that, and a maximum, well, we could put anything here. We can put like 1,000. There's no, I mean, the only reason why I put, well, you can put any number you want here. That's really not important. There's nothing special about 199. I'm going to put it like that and leave it. Single step of 1, that's what we want, and a default value. Here I'm going to put actually a value of 21. We'll see that later why. This is just related. So I want to have steps of 0.1 volts when I scan from -1 to 1. So that's 21 points because we're including the extremes of the range. Okay, so to get 20 equally spaced, sort of 21 equally spaced points, that will take me from -1 to +1 in 0.1 volt steps. And here the push button, I'm going to call this like a do sweep push button, and I'm going to put that here as well. Okay. Yeah, so that's it. So we can go and implement this very quickly. So here, just like last time, now this time, for example, a person actually struggle to remember every time how the class definition is done, but usually the first 3 lines is what you want to copy paste, okay? Because you will have to copy this super, particularly if you're inheriting from Qt widgets. So I'm just going to copy this and paste it and rename the things that we want. So we're going to call this photoresistor experiment. It inherits from Qt widgets, which is okay. Here we also have to save this whole thing. Actually, also I want to rename the window. Instead of form, I'm going to call it experiment. And now I'm going to save this. Photoresistor experiment right there. Just going to remove the .py, so it's now saved as a UI file. Right. So photoresistor experiment inherits from Qt widgets. There's nothing that the class itself needs to inherit. Well, not inherit, but it's inheriting from Qt widget. But I don't need to pass to the class anything because compared to, for example, the Keithley situation, we had to pass an address because that actually matters for an instrument. In this case, I'm not passing anything. I'm just going to use the class to do my experiment. So there's nothing I need to pass in here. Well, actually, that's not strictly true because what I do need to pass are the instruments that I want to use. So actually, that's going to be the power supply, and that's we're gonna actually doesn't go into in it. So that goes into the here. That's where it gets. So we want to pass a power supply and we want to pass a key. Right. So we pass in the, so when we create the experiment, we need to give the experiment class the things that it needs to work. And the things that it needs are the power supply and the key thing. So generally, you'll be passing all the instrument that the experiment is going to use. So now we have to actually assign, this is a bit of a Python syntax thing, but we need to assign these, which we pass the sort of variables, we need to assign them inside the class. So the class knows how to use them. This is a key, sort of a Python specific thing to that we need to do. So self.powerSupply equals power supply. So this becomes now an attribute of the class, self.keithley equals keithley. So we're passing these to the class and then assigning them to class variables, so to attributes. And then we need to do the same thing that we did for the other user interfaces. We need to add the path. Okay, so we need to add the path and then also this UIC load UI. And this is what is going to connect the user interface file to the experiment class inside the in the Python script. So UI file, I'm just going to replace this with the UI file that we've got here. So that's what we want. Photoresistor experiment UI, like that. Let's give me. Yeah, I haven't imported the OS library. I do need that to handle paths. So import OS. Right, so with this, we sort of prepare the interface so we can already test if this works. For it to actually execute, I need to add the experiment user interface inside here. Okay, so we have the Tenma, we have the Keithley. Each of them has their own interface, which is initialized this way. But now, in addition to this, we need to define the experiment user interface. So experiment UI equals photoresistor experiment, and here we need to pass as the arguments of the instance of the class. We need to pass the power supply, which is going to be the my10ma, and then the Keithley, which is the my Keithley. Okay. So you see, I'm passing the same instances of the instrument to different classes. So I'm already using the my10ma in the Tenma user interface, and it's not a problem. We can send this to as many other interfaces as we want. Of course, all these different interfaces will have control over the same instrument, so we need to be a little bit careful not to try and interact with the instrument from too many different directions. Okay, if this is really important to you, you might have to implement some codes to make sure that you're not trying to talk to the same instrument from different places at the same time, because then you might run into some conflicts. But generally, unless your experiment is really complicated, this doesn't really tend to happen. So I'm creating the experiment UI, and then here as well, I need to show it. Experiment UI.show. And now we can execute it and see what happens. In principle, unless we get any errors, we should be getting now 3 windows. There we go. And this is the new barebones window that we just created. Okay, so we have all the 3 windows. And now these values, I mean, we can already start changing them, but they don't really do anything because they're not connected to any actual function. Okay, so that's good to know that works. So now we can carry on. Let me think. I'm gonna do the plotting, maybe. Yeah, let's implement first the first section of the experiment, and then we'll get to the plotting. So that probably makes the most sense. Right. So one thing that we'll need to do is to have so as we imported these. Let's see. Yeah, we imported the user interface. So we have the variables within Python that are sort of the variables that identify the user interface objects. So for example, the spin boxes. So I guess there's different ways to do it. If the experiment is sort of simple like this, what we want is that when I press the button, we're just going to have the script look at the data that I put in my user interface, take these values and use these values to do the thing that I want to do in that particular moment, which is to do the linear sweep. Okay, so we're going to implement a function do sweep, which at the very beginning looks at all the different parameters of the sweep that I've asked for, and that's going to be those are going to be our local variables to do the sweep. So what I'm going to do is so what this helps me to do right now is sort of saves me time in connecting all those widgets with other variables, because we don't actually need to do that. So if the kind of experiment that we're doing is relatively simple, we press the button, the program will look at the values that are in that particular moment when I press the button, the values are in the boxes, and we'll use those values to do the sweep. So I'm going to define do sweep function. The only thing that I will need to connect will be the button. Okay, so I'm going to connect that right now. So I need to check what is the name of the button, which is this. Do sweep push button dot clicked dot connect, and that will be self dot do sweep. Okay, that's so that way we're connecting the button. And here now, what I'm going to do is to define some local variables to run the loop. So we're going to have a v, what's it called? V start, I think I'd called it. Yeah, v start. I'm just going to copy this right away. V start, this is a local variable, equals. And now I'm going to go for self, then v start double spin box, and now I just want to get the value out. So dot value. It's as simple as that. Now this, so when I hit the do sweep button, this is the first thing that's going to execute. So I'm going to put the value that's right now in the vstart spin box in this variable vstart. Okay, so I'm going to do the same for vstop. I'm going to copy paste the same. Vstop. Then we have the number of points. And we've got the same thing going on here. Okay. So we've got all the variables that we need. So what we want to do is a linear scan from vstart to vstop with endpoints number of points, clearly. So I need to create an array, an array of all the different voltage values that I want to sweep. So to do this, we're going to use the very common and very simple NumPy function. So we're going to import NumPy. This is one of the most common libraries that you would normally import when using Python. It just contains like a whole lot. Okay, we're back online. Good. Can you hear me from Zoom? Yeah, I'm assuming you can. Terrible at this. Anyone from Zoom, can you put? Someone. Yeah. Yeah, that's Nico. Ah, brilliant. Thank you, Nico. Thank you. Right. Put this down there. Right, so we've got our variables, and now, so we're going to implement also we're going to, we have to implement the array of voltage that we want to create. So I'm going to call it voltages, numpy dot linspace. This is simply a function that takes a start value, a stop value, and the number of steps. And start, you see here we have the documentation that is already telling me, so helping me out a bit. So stop is going to be v stop. And then we have the num equals to endpoints. Okay, so with this will initialize an array of voltage values. And then I'm going to create a list, currents, an empty list, which I'm going to append when I'm doing the measurement. Okay, so this is just an empty container for now. And here goes the sort of the core of the whole experiment, which is just a simple for loop for V voltages. What we want to do is for the Keithley, we want to use the Keithley dot set source voltage. There we go. And we pass it the value of the voltage. So we pass it the voltage. The Keithley will apply it. Yeah, I forgot one thing, which is it's probably a good idea in the very beginning. So we have to sort of think as the computer will execute these things. So of course, before I start the measurement, what I want is for the key, because I need to, in the Keithley I set the voltage, but I also need to turn it on at some point and turn it off when it's done. So it's a good idea before the actual loop, we set the voltage of the Keithley to be the first voltage in the whole set of values. So we go for self.keithley.set source voltage, and here we set voltages in the position 0. So that's going to be our first value. And at the same time, I want to turn the Keithley on. Self.keithley set output. So we turn on the Keithley. So when we get into the loop, we are ready to iterate over all the different values. Okay, so we set the source voltage, and this will initially, actually, this is not really, well, I'm going to leave this here because if we start the measurement and the Keithley has been left in a certain state before we run the measurement, it might turn on with the voltage, which is not what I want. So I'm going to leave this to start with. I'm going to turn on the output because the output is not something I want to play with inside the loop. That's something I want to control outside. So for V in voltages, set the source voltage. Then I want to do the measurement. So the measured value is going to be equal to self.keithley dot measure current, and that's all I need to do. And then finally, once the value has been measured, I'm going to take the currents list and I'm going to append the measured value. Okay. And in principle, once this is done, if everything goes well, all I want to do is to just turn it off. Self.keithley.output, set output 0. Okay. Now, for the sake of actually just demonstrating this, I'm going to import also the time module, so I can put a little bit of a delay because otherwise we won't be able to see it in the actual sort of happening in real life. So I'm going to put here time.sleep. I'm going to give you a little bit of delay, maybe 0.25. Actually, this goes in seconds, I think. So, or maybe 0.5, I don't know. Yeah, 0.25 should be okay. Right, so I connected the button. When I click the button, it will connect to this function, and we will see if the Keithley does what we are hoping it will. Is what we're hoping it's supposed to do. So I'm not playing. You see, every time I run the script, every time the Keithley window pops up, so I can set these settings separately from this. So of course, in this case, the measurement range of 100 milliamps is okay for what we are doing. Source voltage, whatever. In this case, the source voltage is not a concern. So this window sort of exists independently from this one, and that's fine. I mean, we don't need to interact with it if there's no need to interact with it. So I'm going to minimize it, and let's see. I'm going to run a sweep, and I'm going to have a look here. You can look at the Keithley down here and see if it's actually doing anything or if we get any error. So I'm going to hit the button. So it's turned on and it's sweeping. I can tell you it's sweeping. I mean, there's little digits sort of changing. Nothing's happened really now, but you can believe me that it's done something. So here from the room, I mean, I don't know if you can see it, but anyway, it's sweeping from -1 to +1, and that's where it ends. Okay, so nothing. I can close this. Well, what I could do actually, if I want to just have a quick look at whether the data is here or not, I can make this currents variable. I can make it an attribute of the class. So once I close all the windows, I can go back to the terminal and see what's come out of it. Okay, so in fact, I might actually put this as well as a self.voltages. So we can actually take the values out once it's done executing. So, so I'm gonna close this. Oh wait, yeah. This sometimes happens when you try to interact with an instrument too quickly after you've closed the communication port. We're never closing any communication ports. That would probably be a good idea. There's both Visa and Serial that have a function to close the port. Generally, this is not necessary, I would say, but it's a good idea to implement it maybe as a final thing in your experiment. So we open all these things. I'm going to run a sweep. So it's running. It takes a few seconds. Okay, it's done now. So if I close this, because if I leave this open because it's a graphical interface, it blocks my text commands here. But I've closed the windows, but the classes, they still exist, and the instances of the classes, they still exist. So here I can go to my experiment UI and look for the voltages. And these are the voltages. So it's an array that goes from -1 to 1. And I can look at the voltages and I can look at the currents. And this is a set of values that I got back. Okay, so it's as simple as that. Right. The two look a little bit different because this is a NumPy array, because that's what comes out of the NumPy linspace function, whereas this is a Python list. And that's why the formatting is a little bit different. I'm assuming that comes from that. I could do the same thing, just converting this into an array. So I can go for NumPy dot array. This is just a simple conversion function, and we'll probably print it in a similar way, you see, because it's just a different way of printing. Okay, so that works. So we're happy. I mean, in principle, if you're happy with your experiment, just not doing anything visual, this is all you need, really. What you can add is a function, for example, to save the data. For example, you can use, there's different ways to do it. We're not going to cover that in here, but you can use the numpy.save.txt. And save.txt, that's just it will save a text file, and you can just put in the arrays that you want to save, and then it will save as basically like a CSV data format where you can put your own delimiter. By default, it's an empty space, but you can put a comma, a colon, or whatever else you want, and that will be your delimiter. And you can use a numpy.save.txt function to get your data out, write that to a file, and that's going to be your experiment done. Okay, so in our case, we want to carry on with a bit of graphical interface. So I think that's not going to take too long. So maybe I can talk a little bit further, and then we can take a short break, and then be back to finish that last part. So I'm going to remove this. Now for the, let me see what's probably best to do now. Yeah, we can maybe do this very quickly now, and then we can do the last part of the whole session will be about threading and generating an experiment that you start and stop whenever you want. Okay, so for the plotting, which is what we want to do now. So what I want to do now is once I've done the sweep, I want to plot it. Okay, so I want to see in real time. In real time, once the sweep is done, I want it to be visible as a plot. So for that, I generally use. So I'm going to remove this, and I'm going to remove the delay because that's sleep time. So for this, I use a library which is called pyqtgraph, which I found quite convenient. I don't know whether there's any better ones or different ones. So this is the one that I use personally. I find it quite good, quite convenient. But you might have a look around and see if there's any other ones. But this one definitely integrates well with the Qt interfaces. So it's the one that I'm most familiar with. So pyqtgraph. Pyqtgraph, by the way, it has a very good documentation online. So actually, the page itself has a whole set of tutorials. You can go into the documentation, and there's a whole getting started guide. So there's a lot of formatting things that you might want to do. In my case, I'm just going to demonstrate like the basics. But there's a getting started guide. It sort of goes through a whole set of example, and it's really well made. So if you want to do something a little bit more interesting, more advanced, I recommend you go and have a look at the guide because it's really well written. I'm going to import pyqtgraph, and so what I need to do now is that I need to put inside the interface an object where I'm going to put the graph. Okay. Now, pyqtgraph is not a sort of a Qt standard object. So what we need to do is just sort of decide on a place where we want to put it, and we need to add it from the Python script. Okay. There's different ways to do it. The easiest way in this case would be from the script to actually add a widget. So we generate from the program. In the script, we generate a plot widget, and then we add this plot widget inside the Qt interface. And the way to do it is that you have to take a container, which in this case, for example, can be the widget itself, or I don't know exactly how that whether this will probably work. What I would probably do is that I would put in place an empty layout, for example, in here. And I'm going to call this layout a plot layout. Okay, and I'm going to leave it empty. So then when I can take this from the script, take the plot layout and add a widget to it from the code, okay? Because there's nothing here you can put that will actually be a pyqtgraph object because it's not a standard library. So I just leave this as a plot layout. I leave it there, save it. And so what I'm going to do now is I imported pyqtgraph, and now I'm going to put a function in here to create the plot widgets. In this case, it will be just one. Create plot widget. And here we go for self dot. I need to give it a name. What do I want to call this widget? I'm going to call it I versus V plot. And pyqtgraph dot plot widget. So this is specific syntax for pyqtgraph. So you go in the documentation, you look up how it's done, and this is how it's done. So you call the plot you create the plot widget object, and it inherits from a number of classes of Qt. So it will integrate nicely with anything that is sort of Qt generated. So we created the widget, and now we need to add it to the interface. Okay, so that's what I'm going to do now. So I'm going to go self dot plot layout dot, and now we need to know what the command is, and the command is add widget. And what are we adding? We're adding the I versus V plot. Oops. Okay. And then we need to execute this function, and we can simply execute it directly here. So I'm going to put it right there, self.create plot widget. We just need to execute it once at the very beginning. We generate the plot, and that's it, all done. Okay, so we can see if that works by executing the whole thing, and we'll see if something has changed. Okay, so execute that, and there we go. Okay, so now we have a plot widget. I mean, this already has it comes with a whole range of functionalities, even though there's no data, it's empty, but it's a plot. So we can move around the axis, we can zoom in, we can auto scale, but there's nothing to auto scale to because there's no data, so it won't do anything. You can right click, and here it has a whole range of sort of tools that you can sort of fiddle with your plot. So you can apply some modifiers. You can put it in. You can do some averaging. I mean, it has a whole range of different options that you can add to a plot for the simple fact that you're using a pyqtgraph plot widget. So that's why I find it quite convenient. So it's all sort of taken care for you. But now it's an empty plot because there's nothing there. So what we want to do is to add some data. Okay. So I'm going to close this, and now at the very end of this do sweep function, what I'm going to add is, so I do the sweep, I finish the sweep, and now I've got the data and I want to plot it. So that's what we're going to add. And the way to do this is actually very simple. So you just go for self. At this point, once we execute this, because this is the result of me clicking the do sweep button, this function has already executed. So I just, this object already exists, the plot itself. So I can go for self.I versus v plot, and it's as simple as that, dot plot. Okay, and I go for my self.voltages. And also self.currents. I'm not quite sure. I believe even this is a NumPy array, if you remember from the definition of it, and this is a Python list. I believe it doesn't matter. I think it will work either way. We can try and see. Okay, so every time I do the sweep, it will do the calculations. I mean, it will do the measurements, finish measuring, and then it will just spit out a plot. So let's see if that works. Okay, so we run it. There we go. And in principle now it'll probably be very quick. So you do sweep. There we go. Okay, so this is a plot. You have different styles. So if you want to play with how it's plotted, now this looks as just like sort of 2 points, but actually every one of these is a separate point. I don't think there's a way to change what it looks like once you've executed it. So once it's a widget, that's it. But you can go from the code here, you can set all kinds of different line widths, colors, markers. The background, for example, by default, it's black, but you can make it white or any other color you want. And you can see that I can move around the plot. I can zoom in a specific axis like that. And then I can auto scale to the date. Okay, so this is sort of you see, it's really a few commands, and this already is, for many people, can be already good enough. I mean, if your experiment is always the same, then you need to program it, run it, and spit out the data. That's it, done. Okay, so it's really as simple as that. So we're going to have a quick break now. What we're going to do after the break is implement a start and stop button, and we're going to acquire continuously the current from the key fleet, and we're going to plot the data in real time. Okay, so to do that, we need to implement what's called threading. So we need to run the experiment as a thread that is sort of run continuously and doesn't sort of rip control off me in the execution of the code. Okay, so it's something that I can allocate a thread to the experiment. The thread starts running, and I can stop it and kill it whenever I want. Okay, so that's what we're going to do after the break. Are there any questions from the Zoom so far? Right? Oh, there are. Yes. Sorry, I haven't. Oh, yeah. Okay, that's all done. Any other questions that you might have in this section? Okay, so we'll take a break. We'll be back at, let's say, 3:30. Okay, we'll try and start sharp at 3:30. Okay, let's have a break. So I can just shut this down. Right. So the last thing that we want to do now is all right, actually, just as a comment. So during the break, there was a bit of a question about, which is more about the inheritance and the inheritance and what's the difference between importing modules and inheriting from different classes. So importing a module basically allows me to use the tools that module provides. So for example, I can import, I need an array linearly spaced in values from a starting value and an end value. So I import NumPy as a module, a library, and I use a function of NumPy that gives me the array that I want. And I can use this anywhere in the code once I import it. And so it provides a specific function that I need. And so it really doesn't matter where you use it. I can use it in the main part of the code. I can use it inside the class. Wherever I need this function, I can call it and use it. The thing about inheriting things, which is what you see here, that, for example, the photoresistor experiment is inheriting from the QWidget class. This means that this QWidget class has a lot of the functionalities that I already need, and I need to build up on those functionalities with more functionalities that are specific to my application. So this is different from importing a module because I need to expand on a functionality that already exists by creating a new class. So when I create a new class, so I already have all the functionalities of this class, and these functionalities, I mean, they're not maybe completely obvious, but everything that goes on under the hood with the Qt with the Qt interface, all the buttons, the fact that it connects to names in Python, all these things, the way that the window behaves, that I can minimize it, open it, close it, resize it, all these things are functions which are enabled by the fact that I am inheriting from a QWidget. So if I wasn't inheriting, I would need to basically program all of this from scratch. So you can generally inherit from any class that is inside any of the libraries that you're importing, or you can define your own. So that's the main difference. So importing is for using specific functions that certain libraries have, and inheriting has to do with the object-oriented programming, and it's a way of taking the functionality of a class and expanding on that functionality with new functions. Right. So right, let's get back to the interface. So what we want to do now, so we have a plot window, a graph that we've got within the interface. So we're going to use the same graph. So we can use the same graph and then plot different things depending on what we're doing. So one thing that we've already done is the do sweep function. So we do the linear sweep from -1 to +1. And now we're going to implement another function that will start an acquisition from the Keithley. And specifically, we're going to acquire continuously the measured current. And we're not going to add anything else within the interface apart from a button to start and a button to stop. And we're going to start the measurement, and then whatever the Keithley acquires will depend on the settings of the Keithley. But I don't need to program this separately because I already have a Keithley interface that will always pop up at the same time as I execute the experiment. So what I'm going to do is I'm going to drop in a horizontal layout. I'm going to put one button to start and another button to stop. I'm just going to call it start and stop. You can put whatever you want. Start, stop. And I'm going to put that start _ push button and stop. Right. Okay, so let's get to the code. So this is all I've added, all that's new. And now we have to implement what is called threading. And there are several ways to do it again. The one that I use the most is, and the one that I'm most familiar with is the threading package of Python. So it's as simple as importing threading. There we go. So the way that this works is that I basically assign a certain function to a thread. Okay, so there will be that when I click the start button, I will generate a thread, which is basically like telling like telling Python, look, start executing this, but let me do other things in the meantime. Okay, so it's kind of generating a parallel process, and we're going to see in a minute how this is actually implemented. It's actually surprisingly simple. So I'm just going to do that maybe down here. I will sort of, it's easier if I sort of show it by doing rather than try and use 1,000 words. Okay, so this is a start measurement. We're going to connect this function with the button. In fact, I'm going to do it right away so we don't forget. Start measurement, push button. Well, actually, I might rename actually start the buttons, stop. So we start and stop measurement push buttons. Yeah. Start and stop measurement. Okay, so let's go back here. So I have the start measurement push button and push button. Let me just get the syntax right. So copy paste it. Dot clicked. Dot connect. I'm wondering if, yeah, right. That's what I want. So dot click dot connect self dot start measurement. And I'm going to do the same thing with the stop button. This is all just so we don't forget to put it all in. Now click dot connect stop. Right, good. So start measurement, and so I'm going to write it and then we're going to comment it. That's probably going to be the best way to do it. So I'm going to generate a variable measurement thread equals threading dot thread, and this is where now I have to tell Python what function I want to connect to it, and we'll need to create a function. So the target, this is what the syntax is for this particular library, it will be a function self.run measurement. Which we'll need to define here. So we're going to generate 2 more functions, and we're going to comment all that in a second. Okay. So I'm going to do the run measurement function, and finally stop measurement. Right. So in the run measurement, this is going to be the core of our experiment. So here we're going to put a while statement, so that while basically when we hit the start button, we will generate the thread. The thread will have as a target the run measurement function, and this will then keep iterating over the certain function that we want to do until we hit the stop button. Okay. So I'll show you a typical way that I implement all this, and that's basically using sort of flag variables, so you can communicate between threads. I think it will become a little bit clearer as we type along. Okay. So what I'm going to do for that is that at the very beginning here, I'm going to create a new variable which I'm going to call measurement is running. And at the very beginning, as I initialize the whole experiment, the measurement is not running. So measurement is running is false. Okay. The start measurement function here, I'm going to create the thread. I'm going to put the variable as measurement is running. I'm going to put the variable as true. Here is going to be, I'm just going to put it as a comment, do the measurements and stream the data. Okay, so we're going to fill up this function a little bit later. And here is the stop the measurement. Okay, so why am I doing this whole thing that way? So in the stop the measurement, I'm going to go for self dot measurement is running equals false. Actually, well, I'll carry on with a few more lines. So here is what we're gonna. Here's where we want to put what's the measurement actually doing. So I'm going to put in here a while loop because it's something that has to change during the measurement itself. It's if I use a for loop, it means that I've got a predetermined set of things that I want to do. A while, it will sort of look at a certain condition, and this condition is measurement is running. So if the measurement is running, what I want to do is to measure values. So I'm going to take a measured value, same as before. Actually, we can copy paste from here. And then just before starting the measurement, I might actually initialize, same as we did before, self.current. I'm going to initialize an empty list. And in this case, I'm not running any sweep, so all I'm recording really is the current. So in this particular experiment, okay. And then finally, what I'm going to do is measurement thread.start. Right. And in here, right. So I'm going to type it all down because I guess it's what makes the most sense for me to comment it later. Because otherwise it's difficult to. Here we're going to put the measured value. Okay, so that's pretty much it. So what's happening here, right? The only thing that we connected are the start and stop push buttons, right? So this is what's in the interface. Let's say I want to start the measurement. I hit the start measurement push button. This is connected to the start measurement function, okay? So the start measurement function executes. And what happens? So I create a measurement thread. So I basically assign this run measurement function to a thread. Okay, that thread is I'm just defining it. I'm not doing anything with it just yet. So that thread exists. And then I initialize this measurement is running variable as true. I generate the currents array, the list. This is just a list that's going to contain my data. And then because I'm ready now, I've initialized the list, and so I'm ready to start actually doing the measurement. So I do measurement thread.start, and what this does is that it because the target of the thread is this function, it starts executing that function. This measurement thread is simply a way to start executing a function. But this function will then, because it's a thread, it will start executing in parallel. Okay, so what does this function do? Well, it does this. So the function starts, run the measurement, and this is what I've got inside the measurement. So while the measurement is running, and at the moment it is running because I just set the variable as true, I measure a value and append the value. Okay, and the function will keep doing this until the measurement is running. And because measurement is running is always true unless I start touching something, it will keep running and running and running, and will keep going until something happens. When is something going to happen? When I hit the stop button. So when I hit the stop button, because it's connected, the stop button through my connections up here, the stop button is connected to this function stop measurement. When I hit the stop button, the variable, the flag variable that I set, which is the measurement is running, is going to turn to false. Because that has turned to false, the run measurement function, which has been running all the time in a separate thread, will figure out, oh, hang on, measurement is running is actually now false, so get out of the loop. I get out of the loop, and well, then that's it. It's the execution is done because the function has completed. Okay, so there's really nothing special about this whole threading business. It's simply a way that allows you. So if I wasn't implementing a stop button and I wasn't implementing any threading at all, I would write this, but because the Python console is busy executing this, it kind of takes control off me, and I can't press the button because it won't allow me to press the button because the button will be sort of stuck, you know. So the threading is used as a way for you to be able to interact with the user interface while the console is busy doing something else. Okay, so that's the whole point of threading, and you need it when it's an experiment that you don't have sort of a predetermined way to run. So that's what this whole thing is for. Okay, so we can test this quickly. Right now, it's not going to plot anything because we haven't implemented the plotting on this yet. But we can sort of start, and then we can see the Keithley doing things. I might actually put a little delay again, because that's going to help time, because that's going to help us actually I'm going to put a little delay of a quarter of a second. So people in the room might be able to actually see what's happening, but otherwise you would probably see the Keithley sort of, well, we'll see what you're going to see. Right. So everything looks the same as before, and remember that in this case I haven't implemented actually anything with the Keithley itself in terms of the output being on or being off, because I'm saying, well, I'm going to control all of this from this other widget of the Keithley itself. So I'm going to put the source voltage to say 0.2 volts. I'm going to turn the output on. So now the output is on. You can see the blue LED of the Keithley has turned on. And now I can start the measurement. Okay, now obviously you can't really see much because there's nothing really graphical going on, but I can stop the measurement as well. And now if I close all of it, I can try to access the local variables. So if I go for, what did I call it? Experiment UI dot currents. These are the currents that the Keithley has measured in that time from the start to the stop. Okay, so it's doing something. It's just that I can't really see it. Okay, so that's what we're going to implement next. And that's it. So that's threading for you. I mean, there's really not a lot about it. That's kind of how you use it. So now we're going to get to the graphic side of things. So what we want to do basically is that while this is running, every time it takes a point, it adds a point to the plot. Okay, so that's what we're going to do, and for that we're going to add an additional function. So after the create plot widget, so there was a question also during the break about where am I putting all this code. I mean, sort of in terms of when you're defining functions, where this function is within the class, it really doesn't matter. You can put it wherever you want. Of course, the code executes from top to bottom within a certain function. But this function I'm going to create, I could put it anywhere here, as long as it's outside of another function, and I can't put a function inside another function. I mean, I could do that, but well, that's not usually what you want. So I'm going to just create it here at the bottom, an update plot function. Now here, well, I guess what I would ideally want to do really is to create the plot widget at the very beginning. Let me see where I put this. Yeah, I create the plot widget at the very beginning, and then the idea here is I could. So if I use the plot function, where is it? The one that I used here. So I could use this function, and every time I take a new point, I can do a plot of my current X data and Y data. But this plot function, basically, it will rebuild the whole plot, right? So what I really want to do is I want to plot some data and then just change the data of that plot, right? Okay, so this is, you could do it either way. It's a little bit less resource intensive to just update the data rather than replotting the whole thing. So that's how I'm going to implement it. So here I've got the currents, which is an empty list, but I can still print a list even if it's empty. Okay, an array that's empty is just like any other array, it's just that it has 0 elements, but that doesn't matter. It doesn't prevent me from plotting nothing. Okay, so I'll just plot nothing, and then we're going to add to that nothing data, which will then appear in the plot. So I'm going to call that self dot, for example, I line. That's just the line of the plot. And this is already defined because that's part of the, well, that I'm going to have to define. Let's just have a look. Yeah, so that's the plot function itself. So self, where am I? Down here. That was in the initialization, yeah. So I line is self dot I versus V plot. Well, now actually this will be an I versus time plot, but well, I'm not going to rename it now. It's not strictly correct because I'm not going to plot versus voltage, but I'm just going to use the same. I'm just going to use the same widget. I mean, I could rename this. I mean, the proper way to do it would probably be to rename this into something that doesn't imply I versus V. But I'm going to recycle this variable name. I'm going to put it here. So I versus V plot dot plot. And what am I plotting? Just the data that I've got. Just that right now the data, it's empty. I mean, I've got nothing there, but I can still plot it. So this I line, basically it's the plot object, okay? It's I've got the plot widget. Inside the plot widget, there's the plot object of the actual plot, okay? It's a little bit convoluted, but if you sit down and have a look at it, it all makes sense. So then I've got the line that I've created, and so what I want to do is update that line. So here I'm going to go for self.I line. And this is syntax that is specific to the pyqtgraph library, which is the set data. Okay, set data, and the argument is simply self.currents. I can delete everything else. Okay, so I generated this update plot function, and then I want to use this update plot function every time I collect a new data point. Okay, so that's going to be here dot append, so self dot update plots, update plot. Right. So I'm appending that update plot. So when I execute update plot, I'm going to update the plot with the new data. Yes. Yeah. Yes, definitely. Yes. Okay, so I'm going to execute this and let's see if it all works. I know that there's a little bug that sort of I myself came across when doing these things. I mean, it's a bug. It's a bug on our side because about knowing how this whole thing works. Let's see if it gives us any issues, but I'll show you what's the sort of more correct way to do this, which will basically, it's supposed to work 100% of the time. So in principle, this should already work. Okay. So what have we done? I mean, just to sort of recap, also for myself, really. So yeah, another function that I'm going to add, which I forgot, is to clear the plot when we start a new measurement. Okay, so I'm going to put that right here, self, because if we run this multiple times, we will be stuck with the same plot already plotted, and we'll just sort of start adding on top of it. I mean, strictly, it's not necessary because every time we're sort of readjusting the same data. So maybe in this particular case, we don't really need a clear function, but I think it's a good idea to add it. And you might need it in general. So I'm just going to put it there. Okay, so basically, we hit the start measurement button. This is the first thing that executes. We create the thread. This thread, we could put it anywhere, really. Maybe for the sake of clarity, I might just move it down here, because that'll make it more readable. So we start the measurement. What that means is that we set this flag variable as true. So the measurement is now running. We initialize the current data set. We clear the plot widget, the plot item. We create a new line on the plot, which is in that particular moment plotting just an empty list. And then we create a thread of the measurement itself, and we run the thread. And when the thread runs, what it means that it enters inside this, execute this function, executes this loop. So while the measurement is running, and it's running until I hit the stop button, I get a value from the Keithley. I append the value from the Keithley to the array that I initialized earlier. I update the plot, which means that I change the data on the plot, and then I just have a little delay function here. And when I want to stop the whole thing, I hit the stop measurement button. I set this flag variable to false, and at the next iteration that the run measurement does, it will realize that the measurement is not running anymore, and it will just stop itself. Okay, so that's the idea. Let's see if it all works, and then we're going to get to the final little bug issue that I mentioned earlier. Okay, so first of all, now the Keithley is off because the output is not on. I mean, we've got a zero source voltage. The output is off. But because I programmed this, so it will interact with the Keithley. So it's me, I'm the one, and in fact, this is where the threading comes in. Because this is now in a thread, and it's running in a thread, while this is running, I can fiddle with the settings on the Keithley, which otherwise I wouldn't be able to do, okay? It will sort of lock the interface. So I'm gonna start this, and hopefully you will see sort of points appear. And now if I source a certain voltage, 0.1, I actually have to set it to output something. You see that this is the output, and then I can sort of go up in the voltage. So you see now it's stuck. Yeah, that's the bug I was talking about. So it's still running. So in fact, if I resize the window, you see how it's actually it carries on, but the graphics is stuck. Okay, so this is a little thing that to me personally it took me a while to figure out why this happens. The reason is technical, and I personally myself am not quite so sure why, sort of what causes it, but basically the issue here is that there's something about threading and Qt, okay, so that you want to interact with the graphics with the main thread of your script, okay. As I said, there's only one main thread, which you can see happening. You know, with what we said in the previous if name equals main. So what's happening here is that from a thread that I created inside the main thread, so it's like a sub-thread, I'm trying to update a graphical object that is sitting in the main thread, okay, in the main window. And this you're not allowed to do. So the way that you need to do it is that you have to tell the main thread, look, there's something that you need to do about your interface because it's out of date. Please do it because I can't do it, okay? I don't want to mess you with your order of things. So here, it's a little bit technical, but just I would say, I thought I would put it here because as you can see, this will depend a little bit on the computer and on what you're doing. So that's why it took me a while to figure out, sort of to track down this sort of issue, because I would move to a different lab and a different computer. I would just and the interface would never get stuck, or get stuck a lot less. So it depends on the computer, it depends on what you're doing. But what you want is to basically use some kind of tool that from the main thread, so from the main class definition, will signal the interface to do an update, okay? Instead of doing it from the thread that we're running, and that's the issue that's where the issue comes from, because we are updating the plot from run measurement, which is a function that is inside the thread. Okay, so we need to take the update plot function outside of the thread. And the way that this is done, this is something that is specific to Qt and the whole way that the Qt works. So it's about, I can generate objects that can emit so-called Qt signals, okay? So it's a little bit like when you're pressing the button. When you press a button in the interface, the button itself is generating a Qt signal. So all I need to do is to generate an artificial, sort of a custom Qt signal that triggers every time there's a new point to plot. Okay, so I'm going to do it, and then you're going to see how it works. So to do that, I need to import another little detail. So from pyqt5 .qt core import pyqt signal. Okay, so this is a class, and now inside the general class definition, so not inside any specific function, but inside here, I'm going to create a signal. Okay, so I'm going to create an update plot signal. I'm going to define this as a pyqt signal. And now this signal is basically, imagine as if it was a button, it's just that it doesn't exist as a button. So I can connect this signal to a certain function within my script. So to do that, I'm gonna, well, it doesn't really matter where I can put it down here. Put it down here next to all the connections. So self.update plot signal dot connect self.update plot. Okay. So this signal, now the last thing I need to do is to decide when this signal is supposed to be triggered. Okay, when does this connection actually happen? Okay, and so I need to tell the signal when to, as we say in Qt jargon, when this signal emits. Okay, when is it emitted? And it's emitted when I collect a new data point. So instead of this update plot is going to happen automatically when I connect to the signal, when the signal is triggered. So inside the update plot, I have to go here and say self.update plot signal dot emit. Okay. So you see, it's really 3 lines of code. We imported the pyqt signal class, so we can create a pyqt signal instance, an entity that we can assign a pyqt signal. So this signal is connected to the update plot function, and the signal is triggered every time a new data point is acquired. Yeah. So now basically what I've done is that within the thread, all I'm doing is I'm telling the main thread, look, there's something you need to do. And the thing that you need to do is related to this update plot signal that I've defined. So I'm not updating the graphics from the thread, but I'm just telling the main thread, please update the graphics because I need you to do it because I can't. And so let's see if this now gives us the same sort of issue or not. So we're just gonna let's all close. So hopefully there's no syntax errors. So we'll try and run it. Okay, so I mean, again, this hasn't actually impaired any of the function. I can still do sweeps here. That's still functioning. I mean, this is all running in parallel. Okay, so here I can start the acquisition. I started the acquisition. Everything is off. I can set the voltage to any sort of level I want, and I can turn on the output. And so it's running. And well, the only way to know that it's not going to stop is to run it for a long time. But it seems like it's quite happy to do whatever it's supposed to do. So I can drop the voltage. And yeah, that's pretty much it. Okay, so yeah, it doesn't seem to be stopping, so I'm fairly happy with that. I can turn that off and I can stop the measurement. Right, so as a final thing, we can take the delay out because we don't need that anymore. And we can try to see if our actual experiment from the power supply and the Keithley is successful. So we just rerun the whole thing. Okay, so we've got the interface here, we've got the Keithley. So we're going to set the Keithley to measure with the source voltage of, well, it doesn't really matter. We can give it 1 volt maybe. With 1 volt. And here we're going to keep the supply ready. So you can look at, so here we're going to put a current of 300 milliamps and a voltage. I'm going to start with maybe 1.5. So I'm going to turn on the Keithley. I'm going to start the acquisition. Okay, well, just yeah, that's not quite nice the scale, but you can tweak all the output settings. So see now it's streaming live. So I'm going to turn the output on. So now in principle, I've got my LED here that I'm going to turn on. So I'm going to start raising the voltage, and at some point when it turns on, there's something. So there's a little bit of light coming in, and now as I keep increasing it, I can change the current. Okay, so well, I can keep going, and that's basically my experiment done, pretty much. So I can keep increasing, and then at some point we'll reach the compliance that I've set. So you see that now it's not increasing anymore till we start dropping again. And when I'm happy, and this again, this will keep running because now, because it's a threaded experiment, I can turn off the output and turn it back on, and I can interact with all the other user interface windows without conflicting with the main measurement thread. Okay, and when I'm happy that this is all that I wanted, I can turn that off as well, stop the measurement, and yeah, go home and have a rest. Pretty much, that's all we've got. So yeah, that's pretty much all I wanted to show you, really. There's maybe a little bit of something that you could have included about saving data. There's different ways to do it. One thing that I do recommend to have a look at, the way that I personally save data, is this library that's called H5Py. This is a type of data format that is called HDF5. I personally use it. It's a useful type of data format, particularly if you're using code to then analyze your data. So I didn't include this in the tutorial. Maybe you could have, but it's really quite simple. But I do recommend having a look at it because I think it can improve in some way the sort of how systematically you take your data. And so I do encourage you to have a look at that. And yeah, I don't know if there's any more questions. This is kind of all from my side. So let's see. Right. So yeah, feel free to fire away if you got any questions from the chat. Please, someone else. Yeah. Or from the audience. Yes.
When you calculate the spread, you use the start function.
Yes.
Is there a stop function?
Not that I'm aware of.
So this is like the normal way to handle this?
Yes, I would say so. You can have a look. I'm not actually that familiar. I don't really use the threading library in a sort of a very sophisticated way. The thing is that this the proper way to do it is that the thread should come at its natural end on its own, in a certain way, meaning that there's no sort of abrupt way. I mean, you should program the way that your thread is supposed to end, okay? That's usually, I would say, the best way to do it. There's no there's no kill switch, I would say, for thread, no good kill switch. I would say avoid doing that. So that's why in my case I use these sort of flag variables, and I find that to work quite well. The way to do it, to put it sort of in words, is that you should, when you want to terminate a thread, you should ask the thread to terminate, so it can terminate on its own in a good way. Okay, that's the proper way to do it. There's no way to sort of stop executing code abruptly. Okay, there's no good way to do that. You can handle exceptions. I mean, there's a way. I tried because that's kind of what I thought was the sort of most natural way to do it, but there is no proper and good way to do it unless you program it yourself. So I would say program inside the thread. Think about how it's supposed to terminate, and if you want it to terminate early for some reason, implement a way so you can tell it to do so. Yeah. I mean, one way would be to sort of that an error happens inside the thread throws an error, but then it gets you have to handle the error. You know, there's ways to do it, definitely, but some people do it by raising exceptions. So the thread itself, an error happens, but this error is sort of handled as an exception, and when this exception happens, the thread terminates. Okay, so that's one way to do it. I personally quite like this idea of flag variables, because as long as it's not too complicated, the experiment, you can keep track of them fairly easily. Yeah, and it doesn't sort of leave variables. When a thread terminates, a function terminates, it also sort of releases the memory that it was using, the variables that it was using. So all this sort of finishes cleanly. So that's probably the best way to do it. If you terminate it abruptly with an exception, you have to try and see if there's any more cleanup that you need to do with variables and instances. Anything else? Anything from the chat? It looks like there's nothing there. Okay, well, that's it really. So I'll put this video up as well on YouTube soon, probably in a couple of days. And
if you have to measure the transistor in which the two kids have to communicate to some extent each other,
yeah,
how have you do?
How would you do it? Yeah, so I guess you have options. I guess there's a bit of what I would say like a hardware option and a software option. Okay, so
yeah, the microprocessor in between, maybe.
Yeah, you can do that. I mean, the Keithley itself, most instruments will have a digital output somewhere, like a trigger output. So it depends how you want to do it. So you can do everything from Python. You interact with one instrument, you interact with the other. You make them do things more or less at the same time. That's the thing, you can't control from Python the timings with incredible accuracy. Okay, so you can do it up to a point. Up to the accuracy, I would say probably of the order of milliseconds, which is sort of the interaction time of the communications. So you can take one Keithley, the other, and in the code, you just make them do different things. That's actually, so in my experiment, I often would for example, do that if timing is not particularly critical. But if timing is critical, then you'll have to go beyond that. So not manage some things. You can sort of program them maybe in Python for some settings to do certain things when they receive a trigger. And this trigger you will have to take from some hardware signal. So the Keithley on its back, it's got a digital input-output port. I think it's about 25 pins. And out of those pins, you can pull a cable. And you can have a look in the manual. The Keithley will tell you when it does certain things, or you can program inside the Keithley that when something happens, for example, a measurement terminates, a source value has finished outputting, or it terminates a sweep. I mean, there's a range of things that can trigger an event in the Keithley, and you can program it so that when this event happens, a certain pin goes high or goes low. And in that case, if there's another Keithley connected properly listening, it will notice that this signal has gone high or low, and it will trigger another effect in that Keithley itself. So I'd say, yeah, with the Keithley, it's a bit clunky, this whole thing. You have to program it. But for example, let's imagine you have a function generator and an oscilloscope, and you need to, for example, trigger the oscilloscope to start collecting data when a certain condition is satisfied. By Python, well, yeah, ignore the function generator. Imagine you have an oscilloscope, for example, you need to trigger a measurement to start in a certain moment. You can do it all by Python and interact with the oscilloscope, and at certain point say, oscilloscope, start acquiring now, but the timing of all this will be limited by sort of the speed of the communication with the computer, which is, I would say, of the orders of milliseconds. If you want to go faster than that, you'll need to pull out some kind of usually it's like a TTL signal. It's I don't know what that stands for. It's like a 5 volt or 3 volt signal that comes out of an instrument when it's ready to do something or when it's finished doing something. So that would probably be the way to do it. Yeah. So I guess we'll close it here. I guess I'll stop the recording. Well, thanks very much for listening.